So without further ado, we are going to get started. Our first presenter is Savvas, and Savvas is a PhD student at Lancaster University who is specializing in internet measurement, interdomain routing modeling, and traffic misdirection attacks. Savvas.
Thank you for the introduction. First of all, thank you for accepting me in this meeting. It's my first time here. Everything is so well organized and the vibe is so friendly. It seems like you're not network operators. So, my name is Savvas Kastanakis and I'm a PhD student in the School of Computing and Communications in Lancaster University under the supervision of Professor Neeraj Suri and Dr. Vasileios Giotsas. This is a joint work with Ioana Livadariu from Simula, in which we replicate a 20-year-old paper published in IMC on inferring interdomain routing policies. Now, among the other things that we're going to do in this presentation, we'll aim to answer 4 specific questions. Why would a network operator want to model the interdomain routing system in the first place? Whether the cornerstone model actually captures today's interdomain routing policies? What is the phenomenon of selective announcements and why should we even care about them? And finally, what can be done to enhance our inference capabilities, either as researchers or as network operators? Before jumping into the main point of this presentation, I'm going to explain a few basic things on how the interdomain routing system operates. So, the internet is a network of networks, and these networks are called autonomous systems, and autonomous systems form business relationships between them because they want to exchange traffic between their networks. Even though these business relationships can be very complex, they're coarsely categorized to 2 types: in the provider-to-customer relationship and in the peer-to-peer relationship. In a provider-to-customer relationship, a customer AS pays a better connected provider to transit their traffic to the rest of the internet, while in a peer-to-peer relationship, 2 autonomous systems exchange traffic for free. Apart from the connectivity aspect that business relationships give us to understand the interdomain routing system, we also need to explain those traffic flow rules, the routing policies. Autonomous systems configure their routing policies primarily because they want to achieve their business goals. So, for example, in this toy topology over here, Meta might want to propagate an announcement for a prefix to their provider Cogent, but not to do the same thing to their provider Lumen, because for some reason they want to load balance their traffic or their costs. Finally, autonomous systems are called autonomous because they independently define their routing policies without the need to globally coordinate with the remaining 75,000 or so autonomous systems on the internet. And one last thing is that these routing policies are sensitive information, so usually autonomous systems keep them secret. This slide over here, if I had to summarize it in a sentence, I would like to say that connectivity on the interdomain routing system, or in other words, business relationships, does not imply reachability because, as you can see, Meta is connected with Lumen, but for some reason they do not propagate all of their prefix announcements. Now, let's assume that I'm a network operator and I want to model the interdomain routing system. Why would I need to do that in the first place? There are many reasons. One would be to see the side effects of a traffic engineering strategy that I might follow, or I'm doing some routing policy changes and I want to see how that affects my network. I want to see what would happen in terms of resilience if a large DDoS attack happened in my network, or I would like to find the best geographic location to install the next data center or the next point of presence. So there are many reasons why a network operator would like to model the interdomain routing system. And modeling the interdomain routing system is a subject that has been studied thoroughly the last 25 years. It has been formed as a physics problem, as a statistics problem, as a graph theory, a machine learning, a systems optimization issue. Nonetheless, the cornerstone model was proposed in 2001 by Gao and Rexford, in which Gao and Rexford described a set of rules that need to be followed and met so that the global routing system converges to a safe state. And that work was primarily based on business relationships among ASes. 2 years later, Wang and Gao actually observed the internet routing policies at the time, and they saw whether the ASes of that time obey the Gao-Rexford rules. Now, researchers and network operators over the last 20 years primarily focused on reproducing and replicating the Gao-Rexford model. And to the best of our knowledge, we are the first to fully reproduce this complementary piece of research work to the cornerstone model in an effort to try and understand and answer whether today's routing policies follow this model. This is a replication study, so we follow the exact same methodology which they followed in the IMC 2003 paper. I'm not going to stay a lot here. I'll dive into details later in the presentation. But what we try to do is a two-phase study. Infer the import routing policies of autonomous systems on the one hand, and infer the export routing policies of autonomous systems on the other hand. Now, for the import policies part, we need to define some terms. Now, in the previous example, Meta is a multi-home customer to Lumen and Cogent, and Meta announces a prefix they own to both of their providers. Lumen and Cogent, since they have Meta as a customer, they're going to receive a customer root for that customer Meta prefix. Cogent decides to propagate that announcement to their peer Lumen, so Lumen also receives a peer root for the same Meta prefix. So they now have two roots to the same prefix to decide. And finally, Akamai receives a root from the provider Lumen, so they receive a provider root. The most important thing that happens in the import policies phase is the assignment of a local preference value to those roots. And an autonomous system assigns a local preference value to indicate how favorable that route is. For example, Lumen needs to have a system to decide which route to follow to reach the destination. Gao and Rexford back in 2001 described an ordering between those local preference assignments, and they said that usually customer routes are going to be assigned the highest local preference values because customer traffic generates revenue for your network. Provider traffic incurs a cost, so provider routes are going to be assigned the lowest local preference values, and since peer routes are neutral, they're going to exist somewhere in the middle of this hierarchy. One of the aims, one of the goals of this work is to answer whether this assumption holds with fresh data, 2023 data, because as we said, this is a 2003 work which we replicate. To do so, we need to have the local preference assignments of an autonomous system on the one hand, and the type of business relationships with its neighbors on the other hand. So to get our hands on local preference assignments, we're going to use looking glass server data as well as IRR data. And for the business relationships, we're going to use the state-of-the-art AS relationships inferred by CADA. Now, let's directly jump to the results. We observed that the local preference allocation pattern is consistent with a Gao-Rexford model in 83% of the cases on average, while in the original Wang and Gao study conducted 20 years ago, the average conformance was above 99%. More specifically, even though customer and provider routes are consistent with that hierarchy, peer routes are highly consistent with the Gao-Rexford model. This is probably due to better performance of the peer routes, or most probably because the flattening of the internet hierarchy that happened during those 20 years made the emergence of the IXPs and CDNs, let's say, overtake the ISP's power back in 2003. Now, these results, these numbers you see over here, are extracted using looking glass servers, which are interfaces, either SSH or Telnet interfaces to routers. So you can see the actual control plane configuration. While when you use data and local preference values from the IRR database, which is primarily maintained for documentation purposes, you see a far more consistent view with the business relationships and the Gao-Rexford model. Again, if I had to only say a sentence for this slide, is that local preference allocations today are not as heavily dependent to business relationships as they used to be back in 2003. Hence, we need to reconsider that cornerstone Gao-Rexford model. Now, someone would argue that I'm using inferred AS relationships, so this is a possible bottleneck in my analysis and that I'm introducing some error. We also studied the error introduced by ACE relationships by leveraging BGP communities, and we observed that the error is negligible. So the only thing left that we have in order to explain this inconsistency with the Gao-Rexford model is probably the incapability of the Gao-Rexford model to capture the actual routing policies. Now jumping to the second part of this presentation, the inference of the export policies, things become a little bit more interesting here. We're going to follow the guideline of the original work, and we're going to assume that the provider network will announce, no matter what, all of its prefixes to its neighbors, because that's what a customer pays the provider to do so. However, a customer or a peer autonomous system may selectively announce its prefixes to its providers or peers because they want to load balancer traffic or handle their costs in a better way. And since there is not a specific value like local preference which can help us observe the export policies of an autonomous system, we're going to follow this guideline of the original paper and observe the export routing policies of autonomous systems through the routing tables of their neighbors. Now, I'll give you a slight example of what a selective announcement can look like. In this example, Meta is multi-homed to both Lumen and Cogent. And Meta has two prefixes, P1 and P2. Now, Meta announces to both neighbors prefix P2. So both Lumen and Cogent can access this customer prefix through a customer route because it generates revenue for their company. However, Meta, for some reason, wants to only receive traffic for prefix P1 through the ingress link with Cogent. So they only propagate that announcement to Cogent, and then Cogent propagates it to their peer Lumen. If everything was working based on the Gao-Rexford model, Lumen would follow a customer route to reach a customer prefix. And that is what happens in prefix P2. However, in prefix P1, Lumen is going to follow a more expensive route, which is the peer route, to access that Meta prefix. So if we need to give a definition, a selective announced prefix is a customer prefix received through a peer or provider route. Also, a selective announced prefix can be a peer prefix received through a provider route, but we'll only focus on customer prefixes in this presentation. Now, to study the prevalence and the persistence of selective announcements, we need to have the routing tables of the neighbors of an autonomous system, as well as the inferred AS relationships with its neighbors. Now, what this table shows over here, to the left column, you can find all the vantage points which we used so that we can measure the prevalence of selective announcements in 2023. You can see that the top 5 networks are high centrality networks, and we observe a large portion of selective announcements through the total number of prefixes that they observe. And this slide wants to inform us that the phenomenon of selective announcements is still prevalent even 20 years after the first time it was introduced. Due to time constraint, I won't say a lot in this CDF, but what I want to say here is that if you are a selective announcer and you announce selectively at least one IP prefix, then probably you advertise selectively 100% of your prefixes. Because as you can see here, approximately 75% of the selective announcers announce exactly 100% of their prefixes selectively. leaving prevalence and going to persistence, we study how persistent are those selective announcements. And you can tell whether a selective announcement is persistent if it does not switch from selective to non-selective in a specific time window. We use different time windows, the time window of a day or a month. And you can see on the left figure that selective announcements are consistent during a month. The same figure you would see it in the time window of a day. But on the right-hand side, you see that selective announcements become unstable during a year. And that is a good indication that if you care about compiling selective announcements, probably the best time window would be the time window of a month. We take one step further and we study the persistence of selective announcements over the last 20 years for 5 networks that exist in all those 20 years. And even though you cannot see a clear pattern, you can observe a pronounced median jump in 2007, and that median stayed consistently above 25% for the remaining 20 years, with the highest value of selective announcements being observed by Lumen in 2001 with a ratio of approximately 81%. So selective announcements are sensitive to topological and probably policy changes, so we need to regularly compute them. Now, if I had to summarize in just one slide this presentation, I would like you to know that understanding, predicting, and modeling the interdomain routing system is a crucial function not only for researchers like me, but also for network operators like you. Also, reachability on the interdomain routing system is not only determined by the connectivity we have with other autonomous systems and the business relationships we have with those autonomous systems, but also by the routing policies that they and us configure. And even though we have the tools to observe those actual control plane configurations, and those tools are looking glass servers, for some reason we don't use them. We need to reconsider the Gao export model and extend it with inferential techniques on complex routing policies if we want to overcome this limitation. And trust me, you'll find much more detail in the paper, which you can find in this slide. You can find the code of this paper in our GitHub repository, and feel free to ask me any questions either now or through my email. Finally, before thanking you, I would like you to know that I'm open to research and industrial positions, so feel free to reach out to me. And thank you for your time to watch my presentation.
Thank you. Thank you very much, Savvas, for the presentation. And if there are questions, please go to the mic. I see that there is already a queue for me.
My name is not Stephen Strauss. I'm channeling Randy Bush on the Miracle Q&A. Do you have comments on the 2013 paper, A Survey of Interdomain Routing Policies by Gill, Shapira, and Goldberg, which measured that the Gao-Rexford model held only for about 65% of the relationships?
If we're speaking about the same paper, that was a survey conducted on network operators. Can you repeat the title, please? Because I'm not sure if we're...
The title of the paper is A Survey of Interdomain Routing Policies.
That's awesome. So that's a survey conducted to network operators. So if I was conducting a survey, yes, of course, it's a very important piece of work, but we do not go and actually ask people on their routing policies. We observe them through looking glass servers. So even though actually serving network operators is very important, we also have tools to automate this process rather than asking people in meetings and conferences. Yes, please.
Yeah. Antonio Prado, BGP guy.
I understand.
Did you consider to use RFC 9234 about only to customers and BGP roles, etc.? I would like to firstly thank you for your analysis because this is a very hard field to move.
Yes, unfortunately, I do not recall that RFC, but if you give me some more detail, I might share either my insights because I have some backup slides, or I'll just tell you my personal opinion.
Yeah.
I don't remember that RFC though, no.
Thank you.
Thank you. Okay, we have another question. Yes, please go ahead.
Hello, Sava.
Hello, Pablo.
So during these years, do people change how they define their policies, or it has also changed our view of the internet? So back then we had that view of the internet, we built a model on that view, but maybe today we have more vantage points to see other parts of the internet that we didn't see.
Can you please share your affiliation, please?
Yeah, I'm from Aristotle University of Thessaloniki.
Great. Thank you for your question. So both parts are correct. There are so many confounding factors that can play a role in these changes. But if I only had to summarize in just one thing, what is the main reason is the transition from a hierarchical model, which used to stand back in 2003, in which we had tier 1, tier 2, tier 3 ISPs, so on and so forth. The power was in the large ISPs back then, but based on the emergence of CDNs and IXPs, that hierarchy changed. And we call it a flattening of the internet topology. A lot of ASes decided to follow more aggressive peering policies, either because peering links are less expensive or they have better performance. But the main reason we see those changes, I believe, is the flattening internet hierarchy.
Okay, thank you.
Thank you for your question.
Okay, perfect. So, Savvas, thank you very much for your presentation.
Thank you for having me.
Thank you.